solve this equation, we need to have the width over length, and we have to need use of the NCOX. This is the oxide capacitance, and use again this known parameter. And now we need the gate source, we need the threshold, and we need the drain source. Now, depending on the manner in which the equation is written, some equations replace this with K sub n prime equal to mu sub x COX. So in the lower part equation, you have K sub n prime. You just have to make sure on a formula sheet that that's equivalent to mu sub n C sub OX. So the problem is to the point where we can derive or extract all of each one of these parameters, then we can solve the problem. We'll definitely encounter some problems where it's not so simple to extract the voltages on a Mosfet transistor. Usually this term here can be given in some form. If not, then we have to actually do some calculations of the circuit. So this saturation region, we can decide on different gate source voltages depending upon the amount of gain and amount of drain current that we want to have. So gate to source minus the threshold, if you keep increasing that voltage, you can increase the drain current. This basically is just the same curve. This is an actual Mosfet transistor, and we need to find out where this pinch off occurs on each transistor. So when you design these circuits with a Mosfet, you take these curves, and depending upon your gate source voltage here, you would definitely make sure that your design is somewhere out on these parts of the curves, and then you would stay away from these triode crossover points in here. So and you'd probably design your circuit so that the maximum drain current here, and then by operating probably out here somewhere, you're definitely well protected from getting too close to the triode region. The Mosfet will only amplify when it's in the saturation region. So transconductance parameters, you have mobility, you have the electric permittivity, the oxide thickness, and we have the aspect ratio of the gate, which is the width over the length. Again, some versions of the formula will use the term K prime times W over L. So in the formula sheet, sometimes that appears as large K. And K prime, you may have to actually calculate this component because this deals with the oxide capacity. So K prime is mu epsilon OX divided by TOX, and that's actually the term mu sub COX in the equation. And then at the lower part, COX, we can calculate this. If the terms are not given, then it basically you want to have these sub-formulas so that you can eventually calculate this term at the top. If K is given, that saves time because now you don't have to calculate the oxide capacitance or get into these versions, but just be aware you don't want to make assumptions about this K prime W over L term. You really have to understand what information the problem is giving. And then we'll go over examples of that. So Kn prime, you'll notice here, this term said K prime. K prime can be NMOS or PMOS. So for a NMOS transistor, we would say Kn prime is mu sub n C sub OX, and then the lower says some versions of it. This one is 100 microamp per volt squared, and here's another one, 20 micrograms per volt squared. So if you're writing an equation, this is 100 times 10 to the minus 6, and then this lower one, this is 20 times 10 to the minus 6. So we want to be careful with the exponent as we get more into the math about this. In piecewise, you have Kn prime and Kp prime. However, I believe in piecewise refers both of them as Kp. And you just have to decide, check to make sure, are you dealing with NMOS or a PMOS type transistor. So, cut off for MOSFET, the gate to source of an N channel is less than the threshold. And if that's the case, then the drain current is 0. So this is the first check of the N-channel MOSFET to find out if it's actually been cut off. If it passes this test, then the MOSFET is on. If the MOSFET at N-channel is in the triode region, first it has to be on. The gate to source is greater than or equal to the threshold. And then the drain to source is less than or equal to the gate to source minus the threshold. What this is referring to is a N-channel that's not in saturation. So if we were going to do in saturation, we would have a different set of equations. The drain voltage on a MOSFET, N-channel MOSFET in triode, the gate voltage is, the drain voltage is less than or equal to the gate voltage minus the threshold. And then if we assume triode region, then we will solve this equation at the bottom here. And just keep a note, this says Kn prime, and Kn prime, when we put it into an equation, we'll make sure we carry the exponent units with this. So assuming all of these numbers, we have them, then we can solve for the drain current. MOSFET N-channel and saturation. And as I said, what you're building up is a table of the conditions for a MOSFET operating. And this is definitely a little more involved than a active region for a BJT transistor. So saturation for N-channel MOSFET, gate to source greater than or equal to the threshold. That means the transistor is on, the channel is formed under the gate. The drain to source is greater than or equal to the gate to source minus the threshold. And let's say it passes that test. And then the drain voltage is greater than or equal to the gate voltage minus the threshold. So if it passes these tests here, then we can declare saturation. And this is our equation for saturation. And then we note this square term here, which says, reminds us that this will probably be a quadratic result right here. It's going to have two results, and then we have to decide which of the two is true and which one of the two is false. The P-channel MOSFET and cutoff is the opposite of the N-channel. The gate to source is greater than or equal to the threshold. If this occurs, then the drain current is equal to 0. The PFOS P-channel MOSFET and triode, if this is met, the gate to source is less than equal to the threshold. The channel is formed under the gate, the PMOS is on, and then we need to check these equations. If these three equations hold true, then this is our formula to calculate a P-channel MOSFET in the triode region. And then a P-channel MOSFET in saturation. Again, we have three parameters checked, the gate to source is less than or equal to the threshold. The channel is formed under the gate, the PMOS is in saturation. And then drain the source, we check that, and then we check the drain voltage. And if these are three are true, then this is our current. So in your homework 3, in homework 2 assignment, these are the equations for the PMOS amplifier. And then in the NMOS, in homework 3, homework 2, these are the equations for the NMOS to become an amplifier. Now this term says modulated channel or taper channel under the MOSFET. This is just another side view of the MOSFET. It shows this channel is formed here and now it begins to taper off as it actually goes toward being pinched. And this is termed modulated channel in the saturation region. In order to model that, there's a term lambda that can be included in your equation. That's a channel length modulation parameter. Not all of the equations were included. When we're measuring, what is RO here? What is this term? Exact same equation for BJT.
That's a small cylinder.
What is that term called?
Output resistance?
Output resistance and more early voltage over the drain current, or early voltage over the collector current of BJT. So in MOSFET, in order to model the pinch off, there's a term lambda that can be used. And this equation at the bottom does not have the lambda. So if a problem doesn't actually indicate, use this term lambda, then use just write the equations that do not have the lambda in the equation. Depletion type MOSFETs, the threshold voltage is enhancement type PMOS, the threshold voltage less than 0. Enhancement type NMOS, threshold voltage is greater than 0. Now, depletion MOSFETs are suited for memory devices. These transistors have a channel already under the gate when there's no power applied to the device. So these devices can remember the state that they're in. If they're supposed to be in a one state and the little power, they will stay in that one state. So if we have depletion NMOS, the threshold voltage is less than 0. And if we have depletion PMOS, the threshold is greater than 0. So if we were studying depletion, we would basically go through another group of probably 6 or more equations to quantify depletion type. However, we'll note depletion transistor, the channel in the gate is pre-existing, so DC gate to source is 0. We basically won't be discussing these in this course, but we just want to be aware. We have enhancement type MOSFET, and for memory devices, we have depletion type MOSFET. Now, this is kind of I'm sure we'll be making up our own summary table. I wouldn't just assume these equations here are 100% correct. You want to actually generate your own summary table, and we've gone over all of the equations that are on this chart here. So this upper one is a NMOS enhancement. It has a plus threshold voltage, and the simplest model here is cutoff. If the gate to source is less than the threshold, then the drain current is the source current of voltage 0. So that's the simplest. Now, determining whether it's in saturation or triode. The saturation, we must do these three tests, and then in triode, we do the test that we have here. If it is in saturation, this is our equation to solve for the drain current, and if we determine it's in triode, this is our equation to solve for the triode region. So this example of the NMOS from the version of the NMOS from the homework assignment, and we identify the NMOS by it's an IRF 150. So in PSPICE, and as I said, PSPICE doesn't really give a difference between NMOS and PMOS, and PMOS just calls them KP. So KP is 20.53 microns, and that's 20.53 times 10 to the minus 6. W is equal to 0.3, and there's no units given on that. The length is 2 microns, 2 times 10 to the minus 6. The threshold turn-on voltage is 2.831 volts, and then the early voltage is 100 volts. So it says to make sure to explain your idea of the solution, include use schematics, and show all of the computational steps. So, and that basically is implying that this circuit is definitely going to require several math steps to actually solve. So, run a DC bias on the NMOS amplifier and annotate voltage and currents. Measure the voltage gain of the NMOS amplifier using AC sweep and also using time domain transient. And then part C says, in the NMOS amplifier, assume the NMOS is in saturation, and then calculate on paper the DC parameters I sub D drain current, and then the drain to source voltage, and compare with simulation in the circuit. And then the next says, calculate the voltage gain V out over Vn, V out 1 over Vn 1. So, and this is part of the homework assignment you can basically should already be working on, just entering the circuit into PSPICE, and then determining whether this circuit is in saturation. It doesn't say, or it does say, in part C, it says assume the NMOS is in saturation. However, part C depends upon part A here, because when you run the DC in PSPICE, if that's a contradiction with part C, then the transistor is actually in the triode mode. So you have a version of the schematic here. Let's see, where is the RRF is in the eval library, and in the PMOS version, the RRF 9140 is also in that library. So that's where we find the transistor. Now, the most that PSPICE can do is, assuming the schematic is entered properly, the most they can do is present some numbers. And now, first, we do not assume PSPICE is actually giving the correct result for the problem. This pipe is provides whatever its programmed to do. So if we kind of examine the schematic, when this transistor is biased, is this term correct here? What does 0A mean?
0 amps.
Is that correct? So the meaning of 0A is what?
No current.
0 ampere. Is that correct? Or is that a piece-wise unknown result? And if it's correct, why is it correct?
Because no current goes to the gate.
There's no current in the gate. The gate is electrically isolated. And this is an enhancement MOSFET. It has this icon with these breaks in it. So that means there's no channel under the gate until we apply a gate to source voltage. So when we run this in the simulator, it's going to give it's going to give you the drain voltage, it will give you the gate voltage, and it will give you the source voltage here on this terminal here. So we have all the voltages that we need to actually do a check. So you can now go to the table. We now go to the table and then make the checks that are given here for saturation. And I put some numbers already in the lower part of this schematic. You don't want to take the MOSFETs lightly, because the MOSFETs are 60% of the final exam. That means there could be at least 3 problems on MOSFETs and 2 problems on BJTs. And MOSFETs can be mathematically intensive depending upon the results. But because this problem said to run it in piecewise first and convince yourself that it is operating at saturation, the first part of this problem is you're avoiding to do the math, and you're letting piecewise do the math for you. So after the simulation, the gate voltage is 3.684. So go ahead and write these numbers down. Gate voltage is 3.684. The source is 830 millivolts. The drain voltage is 5.634. And then the threshold turn-on was given as 2.831 volts. So now you have the numbers to check from your table, your formula sheet. So the first check is the gate to source voltage greater than or equal to the threshold voltage. So what is the gate to source voltage?
Is it the 3.8684 minus 830?
So what is your gate to the source voltage here? Now the gate has 2 resistors tied to 10 volts and ground, and it's a voltage divider. So the gate voltage is 3.684, and the source voltage is 830.1 millivolts. So is the gate to source voltage greater than the threshold of 2.831 volts?
Yeah.
3.684 minus 830 millivolts. And kind of to
Yes.
do some of the calculations here.
295.
Okay, so
Oh, nice.
gauge source is 3.684 minus 830.1 millivolts. And you can check this on your calculator. There's 2.853 volts. So is the gauge source greater than or equal to the threshold?
Yes.
Now, the threshold is over here, 2.831. So it's 2.853 greater than 2.831.
Mm-hmm.
It is, it's close to it, but it's still greater than that. So that's we mark that, yes, that's true. Is the drainer source greater than or equal to the gate source minus the threshold? The next test. The drainer source is, the drain voltage is 5.634, and then we subtract the source voltage of 830.1 millivolts, that's 4.8039 volts. So the question is the drain source greater than or equal to the gate source minus the threshold. So the gate source is 2.853, and the threshold is 2.831. So that's the lower equation here. So it's 4.8039 volts greater than. Now it doesn't show the equal sign, but you would use that in a calculation. Is that greater than 2.853 minus 2.831? It's a small number, 0.0229, but it doesn't fit into the saturation reading, and that becomes yes. Now that gives, you can also check the third one, if the drain voltage is greater than or equal to the gate voltage minus the threshold, and you can make that check. Also, this one doesn't really show that third step, but it's basically assuming that it comes out yes, then that means this transistor is operating in the saturation region. So that's so in the assignment then, part A is giving, if the circuit is entered correctly in the P-Spice, part A is giving you the answer to part B on paper. And that's one way to kind of view this part. Your work in part A, which is your simulation, that's giving you enough information to calculate on paper. And once you do this calculation on paper, you'll go back and compare your numbers with P-Spice. So the simulator is predicting the drain current is 830.1 microampere. And if this is actually a saturation transistor, you'll use this equation here. The equation is going to have it's going to be a quadratic equation. And then you'll have to decide which one of the results is actually correct. Now this equation though, I said D is here. What's the unknown in this equation for this problem?
Is it WL?
VGS is unknown. So you're going to be solving for the gate, the source voltage, and then once you get that, you'll get two gate to source voltages. One of the two will probably contradict this. And because it contradicts it, you'll be able to rule that one out, and then you'll take the second one and then you'll solve this equation, and mathematically, you should get a current close to 830 microamperes. And to do that, then most likely the problem has been solved correctly. Now the parts to be aware of in this equation is in the spec, case of P is 20.53 microns, and the width is 0.3 and the length is 2 microns. When you write up the equation for ice of D, most likely you're going to get some really large numbers, probably in the hundreds of thousands, and that's fine. You just have to just be aware of how to actually solve a quadratic equation. So, what we do is here, for your homework, is run it. If you haven't put this circuit into P-space, then you're not working on 60% of the final exam, because a question like this can appear on the final exam. Mosfets, as I said, are really math-intensive devices, and that's basically, you want to be accurate when you actually measure something and you actually get the numbers. And solving a quadratic equation that has large coefficients in it, you definitely need time to actually do that. So for your homework assignment, enter the circuit from homework 2, this problem, enter it into P-Spice, annotate it with currents and voltages, and then check these parameters here to find out if it's in saturation, and then solve for, if you go ahead and solve for the drain current, you'll basically have a start on how to find the gate to source voltage. And here, this would be some, basically some example problems here. So the question, determine a region of operation, and it says it's an enhancement transistor, and the threshold voltage is 1 volt. If it's NMOS, it's minus 1 volt if it's PMOS. And the problem here is giving K is 0.1 milliamp per volt squared. So that's 0.1 times 10 to the minus 3. So to solve this problem, the problem is already giving the gate to source voltage. What's the gate to source voltage here? It's 4 volts, and what's the drain to source voltage?
It's 5 volts.
So the problem is already solved, and now what it's asking to do is go to your table and find out what mode this transistor is in. So on the write-up, it's an NMOS enhancement. The gate to source is 4 volts, the drain to source is 5 volts. If the gate to source and the threshold is 1 volt, if the gate to source greater than or equal to the threshold, so is 4 volts greater than 1 volt?
Yes.
That's true. Now, is the drain to source greater than or equal to the gate to source minus the threshold? So, is 5 volts greater than or equal to 4 volts minus 1 volt? that's also true. And now, because K is given, remember if K is given, that's equal to 1/2 case of N times W over L. So there's a lot of information in this K number here. This problem is given differently. So with K given, you just solve this equation. Is this a quadratic equation?
Yes.
Now, there are no unknowns in the equation though. Gate to source, you solve for it. Gate to source is given. And the threshold GTO is given, so there's no, the only calculation here is subtract from these two. So as far as the quadratic, there are no unknowns here. And we get about 0.9 milliamperes. You want to practice this on your calculator to find out if you are using the units correctly in this calculation. And this is a PMOS transistor, and we can identify it as a PMOS. The source is flipped. The source is flipped upwards. The source is turned upwards, and the current flows from the source to the drain, and it gives some voltage. And this is where errors can occur. What is the gate to source voltage here?
3 volts.
3 volts or minus 3 volts? So it says gate to source. The gate has an inversion on it. The source is non-inverting, so that's a minus 3 to the source. And then the drain of source appears the same way. The drain has an inversion on it in the gate, and the source has a non-inversion, so that the drain then is at minus. How does it get drain the source of minus 4 volts?
The sum of magnetic 1 volt, magnetic 3 volts.
The sum of the gate source and the voltages here. To make sure we understand how we got minus 4 volts here. It's minus 3 plus minus 1. And it gives us a minus 4 volts. So we're using the gate terminal to complete the path over to the source. Is the gate to source less than or equal to the threshold? Is minus 3 volts less than or equal to a minus 1? And the word terminal PMOS, as I indicated, if you're not getting negative numbers, then you're not using the right polarity in your calculation. So this threshold here is a minus 1. And then is the drain of source less than or equal to the gate to source minus the threshold. Now what will, your homework now is going to include completing these problems here. Because going over here now, and you haven't basically taken the engineering time to solve them, we're going to give you an opportunity to do your engineering in this course with this Mosfet. If you avoid the math here, it's going to show up very quickly on the final exam, because these devices are, instead of saying replacing bipolar junction transistors, early memory devices for your jump drive. What's the smallest jump drive capacity you can recall when you first started purchasing it?
jump drive capacity?
smallest capacity.
Um,
Jump drive started in kilobytes,
30K?
Kilobytes. 32K kilobytes. And you would say, what could you put on 32? If you were using it, you learned something to put on those jump drives. But, those drives, Mosfet transistors at those times, in microscopic world, they were big devices. And because they were so huge, even on a microscopic landscape, you could only put so many on a IC. As the technology evolved, MOSFET transistors started to be smaller and smaller, and now your jump drives, now capacity started to increase, and now you're up into a terabyte of capacity, and that's millions and millions of MOSFET transistors. We take for granted when we plug those devices in, and we have a terabyte of jump drive, that drive is immune, basically. It's not immune. Any kind of static that basically gets on the pins that can damage, if even one MOSFET gets damaged, those millions, what happens is the device starts to show an error is on the device. And then the computer asks us, do you want the computer to repair the device? Would you say yes to that?
yeah.
You insert your jump drive, the computer says, something's wrong with this device. Do you want the computer to repair it?
Yeah.
It's risky when you do that because it's going to be trying to do something in the MOSFET arrays to some path that's been opened in the device. So it's going to try to repair something of how it actually searches the device. So keep that in mind. So as far as for your additional homework, and then go through some of these problems here on paper. And these are not, the only problem here that I would say is involved, this CMOS. This problem comes out, well, even that one's not. Okay. This CMOS transistor here, it has a NMOS, and notice that the symbol here is drawn a little differently from PSPICE. It has a 4.8 volt battery on the gate, a 50K drain resistor connected to a micro battery, and then the source is grounded. So the question is asking, what mode is this device in? So we're going to assume for this number here, Kn prime WL, we're going to assume that this is actually equal to 1 milliamp per volt squared. It doesn't really give any problem, but the way it's written. And then that milliamp volt squared will carry over to the drain current. So it assumes that it's in saturation, and it tries to solve the saturation. What's the gate to source voltage on this transistor?
It's a mass of 1.8
What's the gate to source? B gate to source.
4.8.
It's 4.8. Gate source is 0. The gate is 4. So you have everything to solve this equation. There's no real calculation. We'll assume the threshold here looks like 1.2. There's no quadratic equation, and it comes out 6.4 milliamperes. However, calculating the drain voltage, is the battery 5 minus ID RD, and that comes out minus 319 volts. Is that a contradiction? And why? The author here just says X contradiction. Why is that a contradiction?
I'm going to pass it to Anthony.
It's probably a contradiction, not one to dwell on.
Yeah.
It's a large negative number. It's a positive besides the number being large, it says that current is traveling in a reverse direction. As I said, another doing this would probably say maybe the current is flowing in the wrong direction, which is true, even though the number is bigger than the battery. It's a contradiction. Now we have to go to the trial mode. This is probably one that we want to practice on here, because we found a contradiction, we move over to the trial mode equation, and we find that this Kn prime double L is actually equal to 1 here. So I'm going to put the 1 there. And now we solve this equation. The unknown here apparently is V sub drain to source. And the author isolates V sub drain to source as 50 I sub D. So you'll need to understand, study this, find out where this equation came from. And then this is the resulting quadratic equation, 1250 ID squared minus 69 ID minus 5 plus 5.5 is 0. Solving the quadratic equation, I sub D 0.0994 milliamp or it's minus 0.0442 milliampere. And the author decides that this would be a false result because current is traveling in the reverse direction. So there's no need to even solve the problem. So this most likely is the correct one. And now we check the bottom. The drain voltage is equal to the battery minus ID RD, and that comes out 0.03 volts. And now we check, is that less than the gate voltage minus the threshold, 4.8 minus 1.2, 3.6, and yes, 3.6 volts. This is probably the more challenging type of problem because this one comes out with two results. But the part is saying for your homework, develop an understanding how this equation came about, how 5 minus 50 I to D. Apparently, finding the drain of source voltage, the author decided to separate this out into the drain minus the source voltage itself. And in fact, we're actually giving the answer here now. The source is at ground 0. So the drain of source actually is just the drain voltage. And this is the drain voltage here. So what the author is doing is taking this number and replacing the drain voltage with this equation here and here. So that's kind of a hint to how to actually resolving this equation. And this, at least one problem on the final exam will be in Mosfet will possibly have a quadratic results. And I'd say the best, the simplest, the best way to kind of prepare for that is, of course, to review this material in case this almost exact problem actually appears on the final exam, and then also start working, if you haven't, start working on the homework assignment, the NMOS, and then the PMOS. The PMOS amplifier is similar to the NMOS. It has a negative turn-on voltage. I have a question. You notice the PMOS, the source is upwards, and the questions are similar to the NMOS, and I said if the most we can do if you haven't started well on this problem is enter this into PSpice and then start on the DC analysis subject. The grading of the points on these assignments, the largest part of the grading is probably, it will be on the paper design, which is here. So if it's 10 points for this problem, 6 points is probably on part 2, and then 2 points for
And
part A
information.
and B. So keep that in mind
What's
when
the
you
topic?
actually
What's the topic?
work
That you
on
want to
these.
discuss over?
this problem.
Okay.
All right, so let's try to do something with a homework assignment, which is basically to work on a problem like this, and then we'll return to some of these on our next session. All right, that's it for now.